Again, I'd like to introduce myself for those that have just joined. I'm the product manager for the Phocos group. If you have any questions also after the session to me, then you can feel free to contact me about this product or any other product that we have. Okay, so this is the content of today's session. I'll start off with a quick introduction of the devices themselves. We have two at the moment, one which is already released and one which will be released in about 1 or 2 months' time, so quite soon. Then we have 5 use case ideas, so 5 different ways that you can use this product for various scenarios that you might encounter with your customers. We have a list of special features, so those include some features which you may not find on other inverters of this type, or which are very specific to this device and that will just help you understand the AnyGrid a little bit better. Then we have the benefits of this compared to, for example, a traditional setup of having an inverter and a charge controller separate from each other on an off-grid system, or some other benefits as well. Then I'll look at the extensibility, because with these devices we can cater to anything from 3 kilowatts to about 45 kilowatts, because you can hook many of these together. Also, I'll focus on that in the extensibility section. And I would consider those first 5 sections up to extensibility as being relevant for salespeople, and generally for anybody who wants to get a rough overview of the device. And then the last 2 sections regarding system sizing, grounding, and surge protection, those will have to be a little bit more technical. I can't get around that. So again, feel free to leave 2/3 of the way through the session if you feel that it's getting a bit too much. So let's get started with the introduction. We call this the AnyGrid Hybrid Inverter Charger. That's the full name of the device. And I'd like to take a moment to just explain to you what we mean by AnyGrid and why we've used this term for this family of devices. So I'm sure all of you are familiar with the terms on-grid and off-grid. Of course, on-grid refers to typically grid injection inverters, which are there to primarily produce PV power and to either use it directly in your home or to sell all or some of it to the grid. So this typically means that you need to open a contract with your grid operator to be able to sell that energy, and then in return, of course, to get money for the amount of energy that you inject into the grid. So anytime you're working, let's say, grid interactively, so this is parallel to the grid, that's when we consider that to be on-grid. So for off-grid, we can have really completely isolated systems which have no point at all where they touch with an existing public grid. So they could be in the middle of nowhere. They could be voluntarily off-grid by people that are just not willing to connect to the grid, or it might be too expensive to do so, etc. So off-grid can be anything from a small hut in the middle of nowhere to cottages, to homes where it's just not economically feasible to connect them to the grid, or even just for people that are from an environmental perspective not willing to hook up to the mains, basically. So AnyGrid, we're using this term to combine the on-grid and off-grid, and also to have the various intermediate scenarios in between. So here I have a list of some of the different things that come to mind with AnyGrid. So one of them would be unreliable grids, for example. In many countries, we have load shedding, where there's either controlled or uncontrolled power outages, basically. Controlled in the sense that there might just not be enough power on the grid to go around for everyone. So different parts of a city or a town might have their power cut off temporarily to save power so that there's enough to go around. So this is something that you might know ahead of time. You may know that every day, or maybe a day a week, that for a certain number of hours you're going to face a grid blackout. So in that kind of a scenario, something like the AnyGrid will really help you out, because it's essentially an uninterruptible power supply with a whole bunch of other features you'll see later on. Then we can have a regular or sporadic blackout, so that sort of overlaps with the unreliable grids, although unreliable grid could also mean that you might have large swings in voltage or frequency where you just You just need to disconnect to protect your electronics, your loads from facing that. Then we have voluntary disconnection from the grid. So this is, again, for people that, depending on the country and the legislation, it may or may not be possible to basically run an uninterruptible power supply to power your loads. But in this case, to add some PV on top of that. So like that, you're basically using your PV energy when you can. And in that case, you can be completely isolated from the grid. So there's zero risk of injecting into the grid, for example, if you're not allowed to do so, or if you don't have a contract that you've signed with your power company. And you can still make use of that benefit of PV power to bring down your power bill. So that's what I refer to as voluntary disconnection, where the grid is existing and stable, but you're just disconnecting in order to use your own PV power. Then we might have different types of AC generators. So this could be, gensets of any kind, diesel, gasoline, could be a fuel cell, etc., where typically those energy sources are more expensive than PV, especially obviously once the investment has been made. So you want to have those as like a backup energy source, but you don't necessarily want to have them running all the time. Because as you probably know, having a diesel or a gasoline generator running all the time at a very small load, like maybe at 5 or 10%, it's like idling your car. You're basically just wasting fuel most of the time. So it's much more interesting to just activate the generator when you really need it, to then use that to charge your batteries, and then to switch it off again so that you're using it in a much more fuel-efficient way. Then we have taking advantage of changing power grid tariffs throughout the day. So depending, again, on your country or region, you might have different energy power tariffs for day and night. So power might be cheaper during the midday hours, for example, than the rest of the time. Some countries will do that to avoid excess energy in the grid and to put a premium on power when people use it most. So you can take advantage of those price differences. And then, of course, if you're allowed to, if it's legal in your region, you can also use this device to feed power into the grid to sell excess energy you may have. So let's get started with some of the basic specifications of the flagship device, which is the 5 kilowatt, 230 volt AC, 48 volt battery device. So you can see at the top here, we have the name. PSW stands for pure sine wave. H for hybrid, 5 kW for the kilowatt rating, the power output, 230 for the AC voltage, so that's your AC output voltage, and finally the 48V, that's your battery voltage. So you'll see in a moment that we also have a second model, and you'll see that there's some slight differences in that. So I'll start off with the first point, which is we have a 5 kilowatt nominal power rating. So you can use any types of loads. They can be resistive, inductive, etc. Up to 5 kilowatts. Of course, if you're using things like large motors or different types of loads which are not resistive, then you need to take into account your power factor. So typically what you do is, for example, let's say you have a 1 kilowatt inductive load with a power factor of 0.8. Well, then you simply divide 1,000 watts by 0.8, and that gives you 1,250 watts. So that's the rating you should be using. So you always divide by your power factor to get the correct inverter size for your loads. So here we can handle 5 kilowatts. And we have a surge rating up to 10 kilowatts. So it means that even if you have difficult loads which take a large surge to start up, you have several seconds time with twice the nominal power to get those units started up. We have a programmable 220 to 200 volt AC output. So you can select 220, 230, 240 as the output, and you can select 50 or 60 hertz as the output frequency. We can use all types of 48 volt lead-based batteries, so gel batteries, AGM, liquid electrolyte, tubular, whatever, and lithium iron phosphate. You could theoretically also use other lithium chemistries, as long as your nominal voltage and your minimum and maximum voltage are within the limits of the any-grid inverter. If you look at the manual, for example, you'll also see that we have things like equalization charge to to give the best possible treatment to your lead batteries, so that's something you would typically not require for lithium. We have an 80 amp MPPT, which is integrated in the unit with up to 450 volts tolerance of voltage from your PD side. So we have a very high maximum PD voltage for this type of inverter. We also have an 80 amp AC charger. So of course this 80 amp is battery side. So you can use the grid or any other AC energy source to charge your battery. Then we have various communication methods. You can see that on the bottom here, we have this rectangular display unit, and this includes both the display unit itself as well as the communication ports on the bottom. So this whole section is removable, and it's connected to the main inverter by just a standard Ethernet cable that you would find in pretty much almost every supermarket, but at least every hardware store or electronics market. So there's no special requirements for that cable. And you can use that to hook up the display in a different room, for example, to the inverter unit. So you might have a cottage, for example, where you go on vacation, and the inverter might be in a separate room connected to your batteries, and you want to see the battery level and all of the parameters from your living room, and like that, you can just pull a cable between the two. Otherwise, in the unit, in the display unit, we also have Bluetooth Low Energy, so BLE. You can hook up to that, you'll see later, with an app. So you also, like maybe if you're a little bit further away or you don't want to pull a cable, you can use the Bluetooth app as well. We have USB OTG as a method for you to upload battery parameters or to download the data logger, for example, because there's an integrated data logger. We have RS-485 communication, CAN bus, and RS-232, primarily for communication with lithium batteries, for example. And then we have a relay to start generator. When you have low battery voltage, for example, you can automatically start your generator. Then we have that integrated data logger for up to 60 days of data. We have a very short 10 millisecond switchover time between grid and off-grid modes. So this is almost standard for UPS. It's actually a good standard because if you look at most power supplies for computers, for example, they can handle up to 50 milliseconds typically. So we have a much shorter switchover time here between a grid mode and off-grid mode. Then we have an IP21 rating in terms of the environmental rating. So this is an indoor device. And it does have, you can see on the top here, and you'll see a more detailed picture later, it does have a washable dust filters on the left and right as well. So you can just wash those out, and conformal coating on the PCB assemblies. We have a galvanic isolation between the battery and the inverter unit. So this means you can ground the battery, positive or negative if you like, whichever way you desire. And then finally, we have the grid feed-in mode and the battery-free modes as special modes I'll explain later on. So next to this flagship device, we have a smaller brother or sister, which has 3 kilowatts as a power output rating. It's also a 230 volt AC device, and it's designed for operating with 24 volt batteries. So we have half the battery voltage and a little bit more than half of the AC output power. All of the other features you've just seen or heard of, and that I'll explain later on, are identical between these two models. I know that there's a lot of people which are signed on from the Americas. So a lot of you will have 120 volts as a grid voltage. So for you, you'll have to wait a couple more months towards, at SPI we'll present it, and towards the end of the year, we'll be bringing out 120 volt variants of these units as well for your markets. So here's a render of the bottom side of the unit, so you can see what kind of interfaces we have. So I'll start at the top. We have the remote display connector. So if you do remove this display unit, then you connect the Ethernet cable here and on the other side to the display unit if you want to put that in a different room than the inverter. Here we have our relay contacts, which are both normally closed and normally open, depending on where you plug them in. So you can use any logic. We have the USB OTG port, if you want to download data from the device. We have a lithium battery port here, which is designed specifically for use with lithium batteries for communication. And then we have a serial communication port. So if you want to communicate with a computer, for example, or a Raspberry Pi or some kind of existing information system within your building, you can use this port to both query and program the inverter. Then on the bottom, we have all of the power connections and some more interfacing. We have the AC input on the top here and the AC output on the bottom. We have a resettable 40 amp AC fuse or input breaker here. So again, this is resettable. So if it pops out, you can just pop it back in. Then we have the parallel communication interface right here, because as you'll see later in the extensibility section, we can use that to interface with multiple units. Now I have a few questions already coming up here. This is regarding the 240 volts. I was sort of expecting that again, because I know that there's a lot of people from the Americas signed on. The question is whether a split phase is possible, 1 or 2 wire split phase. And the answer for these models is no. You need a real neutral and a live wire. You cannot connect the AC input to 2 live wires as you would in the United States, for example. But the future units that we'll bring out towards the end of the year for the 120 volts, those we are working on to be able to use 2 units in split phase configuration. So you'll still need to connect to the neutral and the line, but you can use them in a split phase 180-degree phase shift to each other. So if you were to really definitely need these units for 120 volt systems, you would have to use a transformer in between for the time being. So here we have the parallel communications, and here we have the battery connectors. They're on the inside, obviously, but the cable pass-through is here. So here's a real picture of the connections you can make. Again, you can see the AC output is here, and the AC input is here. We have the PV input right here and the battery plus and minus here. The terminals that are required here, the cable shoes that you crimp around, because we need big cables here. We're dealing with 100 to 200 amps of current on the battery side to be able to handle those 5 kilowatts or even 10 kilowatts for 5 seconds. So we basically include those terminals inside the packaging from the Inverter. Another question coming in are all the MPPT charge controllers from the inverters, are they individual or are they hooked up to each other? If you use more than one AnyGrid unit, then each one will handle its own PV array. So basically, if you're multiplying the number of devices, you're also multiplying the number of MPPTs. Here you can see a picture of the display unit. So again, this is removable. On the left here, you can see a battery charging source selector for the timer. So you can set up a basic priority scheme. You'll see later what that means. And then you can override that with this button for a certain number of hours per day. Then we have various LED indications, so you can see if the device is currently running in grid or an off-grid mode. You can see if it's charging, and you can also see if there's an error, for example. And then on the right-hand side, we have the AC output source indicator and timer selector. So this is basically the equivalent to your battery charging selector. You can override your standard settings of the AC output source for a certain number of hours per day by using a timer. And then finally here you have an AC output on-off switch. Now this is not to be mistaken for a power switch for the whole device. This will really only control your AC output. So the advantage of that is if, for example, getting back to the cottage example, you might have a cottage which you only visit during the weekend and you're not there during the week. Well then during the week you would turn this off, and then the inverter will still, or basically the unit, the AnyGrid, will start up automatically when the sun is shining, so during the day, and it will charge your batteries. But it will never provide any current or voltage on your AC output, so you can be sure that none of your loads are running. But like that, you can always be sure that even if you're not home, your battery is always kept topped up. So here we have a more detailed picture of the dust filters. There's one on each side. Those are easily accessible from the side. So you can see here there's a single screw hole, and they're just clipped into the side right here. And the actual filter itself is rinsable in tap water. So you don't need to replace those when they do get dirty. So this is an overview of what a system could look like. You can see that virtually all of the components are optional. I'll get into more detail on what combinations make sense in the use case scenarios. But for now, this will give you an overview of what kind of devices or power sources you can connect to the AnyGrid units. So the one thing that is typically not optional is your AC loads. Obviously, if you don't have any loads, then there's not much use for having an inverter typically. So I didn't put optional on that one. Obviously, if your loads are turned off, the device doesn't really care much, but that's pretty much the point of an inverter, is to power your loads. Then we have the PV input, which is optional. We have the battery connection, so you can, but you don't have to connect a battery. So this is already a big difference between the AnyGrid and a lot of other devices out there. And then we have one AC input where you can connect either a public grid, or you could connect an AC generator of some kind, of fuel cell, etc. What's important to know here is that we have one AC input. So if you do want to use more than one AC source, you can, but you need to have an external source selector. So this could be a simple relay, for example, because you don't really need to care about phase shifts when switching over, or being able to switch particularly quickly, because as soon as the AnyGrid detects that there's a problem with the frequency, or that even if it's for a very short time, the grid is failing, which is pretty much what will happen when you switch this over, then it will immediately switch to off-grid mode, and then it will resynchronize to your new AC source, and then it will detect that as a new valid source, and then it can use that. So basically, you do need an external switch, but it takes all of the guesswork out of quick switching and synchronization and all of those other issues. So now an explanation on all of these optional components. So you need to have at least one energy source, obviously. This device is there for converting from one energy source to the other and providing power where you need it to your AC loads. But you're going to have some kind of energy source, and obviously you can have more than one. So you're going to need to have at least one of these, being a solar PV connection, or a public grid, or some kind of an AC generator. Then, as mentioned, the battery is optional. So you don't necessarily need to have one. If you do connect a battery, then of course you use that as storage. The device can automatically act as an uninterruptible power supply, simply because it switches over so quickly between grid mode and off-grid mode. And in fact, when you're working between those two modes, when you're in off-grid mode, so for example, let's say your priority is to use as much PV energy as you can. So you want to voluntarily disconnect from the grid when you don't need it. Well, in that case, you will literally be disconnected from the grid. Both line and neutral will be disconnected from the grid, so there's no risk of backfeeding into the grid. And for this to work well, obviously with your existing loads, we need to have this very quick switch over time, so that you don't have any of your loads which would temporarily turn off during the switch over time. So that just doesn't happen. We haven't met any loads so far that will not handle that 10 millisecond switch over time. For those interested, that's 1/2 sine wave. A question right now is how the MPPT is handled without a battery. I'll get into more detail on that later. And then as an option, with the connected battery, you can feed into the grid if you like. And without the battery, we say that a grid is required. Technically speaking, it's actually not. So even if you have no battery connected, you can still use PV to power your loads. But of course, because now we have absolutely no buffer in the system, and we have no fallback energy source if we don't have a grid connection, for example, then as soon as the PV power drops below the power of your loads, then of course the inverter can only turn off. So this is not recommended. That's why we write that a grid is required. But technically speaking, it would work without a battery, even and without an AC source. So obviously the big advantage of working without a battery is that you can save that cost of investing into a battery. Or, for example, you could start off without a battery and you might say, okay, PV has gotten relatively cheap as compared to maybe 20 years ago, but batteries are still quite expensive. So you can start off with the AnyGrid, you can hook it up to your existing home, and then you can just add a battery later as they get cheaper. And then finally, if you're working without a battery, you can still obviously take advantage of your PV power. And if you do have any excess energy, so if you're producing more power from PV than you require for your AC loads, then it's up to you if you want to inject that into the grid or not. So there's a specific setting for that. If you're not allowed to inject into the grid, for example, then you would just leave that disabled. So now I'll move to the 5 use case idea. Another question, I think it's easiest if I just answer the question as I go along, is whether anti-islanding protection is available. It cannot, because it wouldn't make any sense. The whole point of this device is to be able to work off-grid, which by definition is an island. So when it disconnects from the grid, it's galvanically isolated from the grid. There's no connection between neutral or line and the grid, and that by definition is an island. So you cannot really compare this to a straight feed-in inverter, where it's vital to have anti-islanding to not inadvertently create an island when the grid has failed. That's not really comparable here, because when the grid does fail, or when the grid goes down, then the device automatically switches over to off-grid mode, which by definition is an island. So use case number 1, this is an off-grid use case, so you can see that there's no grid connected here. We do require a battery in this case, and you're going to need either PV as an energy source or an AC generator like a genset, for example. You can start that automatically by the relay described earlier. So the benefits of this kind of system is that you have a vastly simplified system as compared to your traditional inverter plus charge controller plus potentially charger from the grid. So you're combining at least 3 devices into one, and that's not to speak of the whole synchronization and fast switching, etc. So you're really simplifying that down into a single device. Also, you have no requirement to coordinate communication between multiple devices, because there's no need to have a separate charge controller or a separate inverter anymore. So the only multiple devices you might have is maybe more than one AnyGrid, and in that case, the communication is baked into the devices, of course, so they can handle that between each other. So there's nothing you need to do in terms of protocols, in terms of baud rates or fabricating cables, etc. So use case number 2 is a grid-connected scenario, so an on-grid scenario with battery and PV. So you would do this, for example, if you want to prioritize solar for electricity cost savings, so to save money on your power bill. Or you could even do the opposite. If you say that the most important, the highest priority for you is to keep your battery charged at all times for the case when the grid fails, then you want to have the opposite. Then you want to prioritize the grid. You want to use the grid whenever possible, and you want to use all of the energy to just keep your battery topped up. That is theoretically also possible. And of course, you can have various scenarios in between the two. If it's legal in your area, you can feed in as well in this scenario. But it's physically impossible to activate this function by accident. You'll see later how it's activated. So the benefits here are you can save electricity costs by simply prioritizing PV and just disconnecting from the grid when you don't need it. And then again, if it's legal, you can sell any excess energy you might have to the power grid if you have the contracts for that. Then use case number 3, again on grid. This time we have a battery, but we have no PV. So even in cases where you don't have access maybe to the roof because you might be in a multi-story building which is not your own, you have an apartment of some sort, etc., you could still use the AnyGrid basically as just a large uninterruptible power supply. The way you would have in front of just a computer, well, you see this as a large one which will act as a UPS for your entire home. So in this case, you benefit from the fast switching between the grid and off-grid modes, and you can be sure that your home is still running even if the grid fails. Obviously, in this scenario, because you have the public grid as your only energy source, the system is only as good as your battery. So obviously, when the battery capacity is depleted, then at some point the inverter will have to turn off. But it's definitely good to keep you running for probably several hours, even if the grid does fail. So someone is asking if this can be AC coupled. I believe what you mean by AC coupling is connecting a grid injection inverter on the AC output. That you cannot do. So the AC output is unidirectional. It's only for providing power to loads. It cannot accept power from a grid-connected inverter that you would connect it. So use case number 3. We have an on-grid scenario this time with a battery. Sorry, we just had that. Use case number 4 is on-grid with PV, but without a battery. So this time, why do we want to do this? We want to use PV power as well as we can, again, to push down our energy costs from the grid. We can still feed in if it's possible or legal in my region. Again, it's impossible if it's not activated. And then this is basically equivalent to a grid-connected inverter, except that if you want to connect with a grid-connected inverter and you're not allowed to inject, for example, then you would need an energy meter. You would need to make sure that you have a communication between your inverter and the energy meter to just make sure that you're never backfeeding anything into the grid. So you can avoid all of that by just connecting all your loads to the AnyGrid, because it will handle all that for you. It will make sure inside that it's not backfeeding into the grid if you don't have feed-in activated. So the benefit of this use case is that you don't need to invest into batteries, but you can still use PV power as required to reduce your energy costs. And then obviously you still have this possibility later to add batteries if you like, or if the battery prices come down, to then later add that UPS and off-grid functionality that of course you can't provide without batteries. And then finally, use case number 5. Which is again on-grid, and this time with a backup generator. So this is like your maximum system in a sense, at least when you're using a single inverter. So in this case, you would require an external energy source selector, as I've described earlier, which is the part right here. Because we have a single AC input, we need to have some way of isolating multiple AC sources from each other. But again, the AnyGrid takes the guesswork out of quick switching, out of synchronization, etc. So here the benefit is really guaranteeing power to your loads under all conditions. You might have the grid that you can use. You can obviously prioritize PV if you wish. And even if the grid fails and it's in the middle of the night and you have a small enough battery to not get you across the night, then you can still automatically start the AC generator as required to power your loads and potentially charge your battery from the AC generator as well. So now for some better understanding, I'd like to look at some of the special features of the AnyGrid devices. So the first one is a closer look at the AC output source priority. Now, there's a lot of text here, and I know it's not good practice to put a lot of text on slides like this, but I want to make sure that when we give you this presentation and send that to you as a PDF, that you can also use that to look things up and to get a good idea of how things work, as opposed to just having a single webinar, and then maybe later if you want to look something up, then you might not remember what was being said. So don't worry, you don't have to read all of this. I'll explain it to you now. It's just for your information for later, and of course that goes for the entire presentation. So The AC output source priority, I think, needs some explanation for you to grasp how this unit is deciding on the various priorities. So we have three options, which are listed here. We have USB, SUB, and SBU. And those acronyms stand for the order of the priority. So we have utility solar battery, then we have solar utility battery, and then we have solar battery utility. So let's start off with the first one, the utility solar battery. So this is the scenario where solar isn't actually that important to you, or you might have a very small PV array just to keep your battery topped up or whatever. But basically, the reason you're using the AnyGrid is to handle handle scenarios where the grid fails. So in that case, guaranteed power is more important than the cost of power, for example. So in that case, you want to prioritize the grid or the utility as a first priority. You'll use solar if the grid fails, and then battery to make up for if you don't have enough solar power. The second priority is, or the priority option is solar utility and battery. And this one will prioritize PV as your first priority. So whatever energy you're producing from your solar modules, your solar panels, you'll be able to use that directly for your loads and obviously charging your battery at the same time. And as a second priority, you're using utility. And in this case, we don't have a hard switchover between the grid and the off-grid scenario. But instead, what we're doing is, let's say you're producing 1 kilowatt from your PV, and you need 2 kilowatts for your loads. Well, then 1 kilowatt will come from solar, and the remaining kilowatt will be mixed in from the grid at the same time. So there's no hard switching in this scenario. And only if those two are not sufficient, and it's obviously it's up to you, there's a parameter setting, you can decide how far you want to discharge your battery before this happens. But at some point, if you're producing less energy than you're consuming between solar and utility power, then it will automatically switch over to battery, or basically as soon as the grid fails, it will automatically switch over to battery mode. And then it will simply discharge your battery as long as it can to provide power to your loads. Of course, if in the meantime you have enough PV coming in again, PV will then increase the battery voltage again to keep your battery topped up. So this middle scenario, I think, is most useful for Western countries where you have a more or less stable grid, but your priority is you just want to save power on your utility bill, and maybe you don't want to cycle your battery, for example, because that's what you would essentially be doing in this scenario, is you're reducing the cycling on your battery. And the last one is if you really want to have every watt of power that you produce in your PV array, you want to use that as much as possible. And to do that, you're not only using your solar power, but you're also discharging your battery. And again, it's up to you how far you want to discharge your battery on a regular basis. But in this last scenario, you are specifically using your battery, you're cycling your battery to make the most of your PV energy. So for example, in the evening, when the sun has set, you still purposely want to use power that you've stored throughout the day from your battery for your loads. So that's this last scenario where, again, you want to prioritize PV to save utility costs, and you also additionally want to make the most use out of your battery to be able to capture every watt hour that you, or to be able to use every watt hour that you've captured from solar. Next, we have the battery charger source priority. So really, there's only these two priority settings that we need to operate efficiently. The first one was deciding how your AC output is powered. So how are your loads powered? At any one time, are they powered by solar, utility, or battery, or all three? Or at least two of those three. Now here we're talking about the battery charger source priority. So this is a bit different, the setting, in that this is not how we're powering our loads directly. This is now we're deciding how we charge our battery. So for example, we might purposely not want to use the grid to charge your battery because then we're just shuffling around power. We might use only PV to charge our battery because the battery is only supposed to be a buffer for the solar energy that we're consuming. So this setting is more or less independent from the previous setting. So here too we have three options. The first one is solar first. So basically, if there's solar energy available, regardless of how much, that will be used to charge your battery and nothing else at that point in time. As soon as the sun sets, or if we have, for example, snow on our PV array, or if really there's no energy coming in at all from solar, then the utility will be used to charge your battery. And you can change the setting on how much current you want to take from utility for charging. So you can use a small setting for that. You can say, okay, I only want to charge from utility with 10 amps. And when the sun is shining, you can charge with up to 80 amps, for example. Then we have the solar and utility, where we're using both simultaneously to charge the battery. And then finally, we have the only solar setting, where we're absolutely forbidding any charging from happening from the AC input. So I think the last one is quite obvious. We're just completely disabling charging from the AC source. But I do have a small warning for you. And that's described in this text down here. Basically, the AnyGrid needs to power itself, of course, to be able to provide the AC signal when it's in off-grid mode, etc. And it does that from the battery terminals. So it will power itself from the battery side. So now, conceivably, what could happen if you're living in a region where you might have snow during the winter, obviously that depends on where the system is installed. It's not going to be a huge issue around the equator. But if you're living in North America, for example, or in the mountains, it will be. And let's say you want to only use solar energy to charge your battery. Well, then you would take the only solar setting, for example. Or what will happen is eventually, if you do have snow on your PV array, and there's literally nothing at all coming in from your PV side, well then, slowly but surely, the AnyGrid inverter will drain your batteries over a long period of time. And to avoid that from happening, we recommend that you do not use this setting in those scenarios where you could have snow on your PV modules, for example, but that instead you use the solar first setting. So you can be sure that during the day when the sun's shining, there's definitely nothing charging the battery from the grid, only from solar. And then when the sun is not shining, so again, for example, if there's snow on the roof or also during the night, then the grid will be used for charging. But then you can use a very small charging current, so only 2 amps on the battery side. So that's like around about 98 watts, roughly, that you're allowed to charge from the grid. And what that will do is it will offset the self-consumption of the AnyGrid, and at the same time, a little bit more to just like almost trickle charge your battery with 1 amp. So you've seen the 2 priority settings. It really is that simple. You'll see later you can still override those 2 priority settings with timers, but that's like your basic configuration that you need to set up. Those are like the 2 most important settings because they will define what use case is valid for your particular system. So now we look at the overload bypass as a special feature. So you might ask yourself the questions, well, as opposed to a grid inverter, which is connected in parallel to the grid, where basically if you exceed the power rating of a grid inverter, it doesn't matter because automatically you will be pulling that power from the grid. The downside from that is if you're trying, because nowadays obviously there's a lot of grid connected inverters which have storage as well. I've seen several times, and there's a lot of, I'm based in Germany, so I visit a PV symposium once a year. And actually we had, I think it was the Fraunhofer Institute, which was looking at least 10 different grid-connected storage systems. And what was very interesting is they were very slow. In the sense that, let's say you have a 2 kilowatt load, for example, let's say a vacuum or something. And of course, you want to prioritize your PV power. That's typically the reason why you install a grid-connected storage system. So you will want to provide that 2 kilowatt out of your battery if the sun isn't shining, for example, at night. And what will happen is it'll take a certain amount of time for a grid-connected inverter to realize that it needs to power this 2 kilowatt load, not from the grid, but instead from the battery. It needs to basically power up the whole conversion from your DC battery to the AC, etc. And this might seem strange to you, but this will take anywhere from half a second to a second up to 1.5 minutes, which is, of course, insanely long. So there's really a lot of even like market leaders out there which have very slow systems, in the sense that if you can imagine, for example, if you're cooking something and you have a heating element which will turn on and off maybe every second or every few seconds, that this type of system will not be able to cope with that load. It will do, like, sometimes it will accidentally inject into the grid because, well, your load has turned off and it's trying to provide 2 kilowatts now. And the opposite will happen as well. You're consuming 2 kilowatts and the system just hasn't caught up. It's not taking the 2 kilowatt out of the battery, but instead it's coming out of the grid. So this kind of thing cannot happen with the AnyGrid if you're working in off-grid mode. Because obviously if you're disconnected from the grid, well then there's no way the grid can provide any energy at that instant in time. So this is a very different beast, in the sense that this inverter will react within literally milliseconds to your loads, because it has to, because otherwise the voltage would drop. So that's basically the difference between a grid inverter and this AnyGrid inverter, which is actually based more on an off-grid inverter. But to make a long story short, I want to get to what the overload bypass does for you. Well, if you're connecting your loads on the AnyGrid, and the AnyGrid is basically potentially disconnecting your loads from the grid, it means it's in between the two, so it's in series with your loads. So it means that all of the power flowing to your loads has to flow through the inverter, has to flow through the AnyGrid. So the questions you might ask yourself is, well, what happens if I try to take more than 5 kilowatts out of the AnyGrid? And that's a very valid question. That's why we have the overload bypass. So basically, let's say you are in the scenario where you have a connection to the grid. Obviously, if you don't have any connection to the grid, and you don't have any other AC source, well then if you're overpowering your inverter, it can only shut down to protect itself. If you're demanding more than 5 kilowatts for a long period of time, the inverter will simply turn off. If, however, you do have an AC source which is capable of sustaining the 5 kilowatts or more than that, well then the inverter, if you activate the overload bypass on the AnyGrid, then as soon as it senses that it's no longer able to cope with your energy demand, it will simply switch to grid mode. And then basically it's just bypassing the whole inverter entirely, and it's just passing the power directly from the grid to your loads. And it can do this very quickly, same speed as typical switchover times of 10 milliseconds if you're in UPS mode, which you probably are in most cases. And then it will provide you with up to 40 amps of AC power. And if you multiply that together, 40 amps times 230 volt AC, that yields you around 9.2 kilowatts of power that you can pull through the AnyGrid. So it's almost twice its initial power rating, or its nominal power rating. And in fact, for the 3 kilowatt, the smaller model, it's also 40 amps. So you could theoretically pull up to 9.2 kilowatts out of the 3 kilowatt model, simply because it's passing the grid power through to your loads if you exceed the 3 kilowatt nominal rating. So you might ask yourself, well, what happens if I exceed even that? Well, then at some point, because the power is flowing through the inverter, it has to protect itself. At some point, the traces, the cables would overheat. So we have an integrated resettable fuse, which I showed you at the beginning of the session, which will simply pop out if that risk happens. And then, well, it's up to you to just put it back in. There's no need to buy any fuses or anything, but that's just like the ultimate layer of protection for the AnyGrid to protect itself. Now I'd like to go into the methods of battery current limitation. Now, depending on what kind of battery you're using, I know there's a lot of pressure from the market and from customers to choose the smallest possible battery. Technically, that's not a good thing. Economically, I understand that, obviously, because batteries tend to be by far the most expensive portion of a solar system. if there is a battery included in the system. So typically, in at least a real off-grid system, a battery will make up like 50 to 60% of the total system cost. So that's obviously a huge chunk. So people will try to, even if they're using a battery, they will try to keep it as small as possible, simply to save that money. And in order to work with that, we need to be able to limit how much current is going in and out of the battery at any one time. Because if there's a tendency to take batteries which are, well, almost too small for the system, then we need to figure out a way to get power from elsewhere so that we don't overload the battery. So in that case, basically the battery is too weak compared to the 5 kilowatt or 3 kilowatt, depending on what model you take, that you're trying to provide to your loads. So we have this split up into the charging and discharging current. So the charging is relatively simple. Typically, you'll find regardless of whether they're lead acid batteries or lithium battery, you'll find a maximum charging current. So let's say, for example, your maximum charging current is 40 amps for this particular for a particular example system. Well, then you can just go into settings menu number 2, and just for your information, there's about 35 settings roughly on the unit, 35, 38, something like that. So not hundreds of settings, so it's actually a lot easier to set up than a lot of other devices. But I think the settings really do make a lot of sense, and they still keep things as simple as possible. So in settings menu number 2, you can limit the total charging current. Now, regardless of whether you've set a priority to charge from PV or from grid or from both, this is like a total cap. It will add together your charging from PV and from AC if activated, and then it will simply cap anything higher than, for example, 40 amps, to make sure that your battery is not receiving too much charging current. Too much charging current can cause, well, several things, but 2 main things would be overheating the battery is the obvious one for lead acid batteries, or if you're using lithium batteries, then it's not worse, but it's worse for the system, but it's better for the battery. Typically, if you have a battery management system inside, then you will need to, the BMS will simply notice that there's too much current going into the battery and will simply shut down. So basically your battery will just turn off if it's well protected, or it could even be damaged if it's not well protected. So this is an important setting if you're using small batteries. You can limit the charging current that's going into the battery. Taking current out of the battery, obviously to power your loads, is it's a little bit more difficult because if you're in a pure off-grid environment and you have no AC source, so you just have PV, a battery, and your load. If you're exceeding the maximum current of your battery, there's no other energy source. Like obviously if you're using PV, then all of the PV power is being piped automatically right to the loads. That's always the first priority. It's just the way the unit is set up. And then anything that's missing would come out of the battery. But at some point, if you're overloading your battery, if you're discharging with more current than you can set up here, well, the only thing the inverter can do is shut down to protect your battery. I think what's more interesting is if you have an AC source. So for example, if you do have a grid connection, then this is very similar to the overload bypass I discussed before, where if you overpower, like you're demanding more power than the inverter can deliver, then it will automatically switch to the grid temporarily. Well, that's the same thing will happen here, except now you can decide at what discharge current that happens. So before it was just a pure power thing, where if you exceeded the nominal power of the unit, it would switch to the grid. In this case, you can say, well, at, let's take the same 40 amps, for example. My battery can only handle 40 amp discharge current. Then you can, in settings menu number 41, you can just set that up. And then automatically, as soon as it detects that your battery is being discharged with more than 40 amps, it will temporarily switch over to the grid. Obviously, if the grid is available. If it's not available, the only thing you can do is shut down. What's important to know here as well is that, well, depending on how you size your system, this shouldn't happen if you size your system well. This whole overload bypass thing, or in this case, if you limit the discharge current of the battery, That's not to say that this should happen like 50 times a day. Obviously, this is a hard switchover, so we have two relays which are involved, which are relays that try to switch at 0 volts. So obviously, in your sine wave, you're always working between in a 230 volt system between, it's actually more like 250, 260 volts plus and minus, and there's always a 0 crossing point, and that's when the relays switch. But relays tend to be slower than for example MOSFETs or things like that. So this is like a protection of your battery, and potentially for the overload bypass of your inverter. It doesn't mean that it should happen many times a day. This is just to ensure that your loads are always running, even if for some reason somebody turned on like the 3 most powerful loads at the same time. So just keep that in mind, that this doesn't mean that you can put like 8 kilowatts of loads on your inverter and it doesn't matter if it just switches back to the grid 20 times a day. But even if it does, there's a timer, so it's not going to flick back and forth all the time. It's going to stay on the grid for several minutes and then come back if possible, if the power requirements have settled down. Now we have the priority timers as another special feature for these devices. So I've explained the AC output source priority, so what you're powering your loads with. And then there was the battery charger source priority. So both of those are important to set up, let's say, the basic functioning of the unit. But now you can go in and actually override those settings for a certain number of hours per day. So this, I think, is particularly valid as a scenario if you really want to, for example, force something during the night, or you know exactly that there's like a huge load which normally you don't have, but there's a huge load which will turn on at a certain time every day, so you just preemptively want to switch to the grid or whatever. And I think that the most valid scenario, the most common scenario, will be when people have different power tariffs throughout the day. So again, my example from the very beginning of the session, in some countries in the middle of the day, when actually there's not a high demand for power, but there's a lot of production, there's a lot of PV systems which are injecting to the grid, so the power can be very cheap then. So here you can say, okay, yeah, let's say from 11 o'clock in the morning to 1 o'clock p.m., I want to automatically charge from the grid my battery because, well, if my battery is not full at that time, energy is so cheap, I really want to have that energy for later because then I can get through the night because maybe my battery is a little bit undersized. So in that case, you can simply set up the battery charger source priority on the bottom here, and you can set it from 11 to 1300 hours, and like that, it will just temporarily switch the battery charger source priority to the grid, for example, for 2 hours every day. And another special feature, and this is a big one because this is very rare among, let's say, off-grid oriented inverters. You'll find virtually all of the competitive products, they absolutely require a battery to function. The whole setup is around working with a battery. And in this case, we have a very special topology for this unit, which actually allows functioning without a battery. So again, I very strongly recommend that if you work without a battery, you do have an AC source, so typically a grid. But theoretically, again, even if you don't, what will happen is it will try to balance the PV power against the AC output power. So of course, if the PV power is lower than the AC output and you have no battery and no other energy source, so you have no buffer and no further energy source, well then of course the inverter can only turn off. But if you do have the public grid, then the PV modules will deliver as much power as they can, and anything that you require above that will automatically come from the public grid. And in this case, it's without a switchover. So in this case, we are working in parallel to the grid, where still, if you don't have grid injection activated, we are still ensuring that you're feeding in 0 into the grid. And we're doing that by always taking a small current from the grid to avoid any reverse feed-in. So that's the second last point here, is that we're always ensuring that we take about 80 to 100 watts of power from the grid to make sure that there's no reversal of power to inject into the grid inadvertently. And then one of the last special features I just want to outline here is the grid feed-in, because we don't have that much time left. We have about half an hour left. We have the grid feed-in feature. I think, yeah, it's obvious what it does. As soon as you have more power that then you can either use to charge your battery or to power your loads, that means you have excess power, and then you can sell that power to the grid. In order to do that, you go into settings menu number 8 to enable grid feed-in, and you will require a PIN, and this is important so that you don't activate it by accident. A lot of grid operators would be very unhappy if you could, and you will get that PIN number. It's a 4-digit number from our support team. Now there's also Phocos Link, it's called, a mobile BLE app. This one is about 85% completed, so we're just actually testing it right now. We've developed it fully ourselves, and this will be available on Apple's App Store and Google Play within the next 4 weeks, roughly. That's our current target. So you can see here that will give you a monitoring solution, a local monitoring solution of the device. It allows you not only to see the current state of your system, but it also allows you to program some of the settings of the system. Now let's look at some of the benefits. I'd like to compare this to discrete system components. So traditionally you would have, if you're working in an off-grid system, you would have an inverter, you would have a charge controller, maybe you have a charger from an AC source like a generator or something. Then you need to hook all of those components up to each other, make sure they speak the same language, take care of synchronization, all those other issues. So compared to that scenario where you're really taking one component for each function, we have a much, much lower cost in this system. I mean, we're talking for the 5 kilowatt AnyGrid, we're talking $999 as an end customer list price. So if you compare that, buying an 80 amp charge controller, an 80 amp charger from the grid, 5 kilowatt inverter, and all the other stuff you would need around that, we're talking a fraction of the cost. We're talking a third, maybe a quarter of the cost. Also, we have a much, much easier installation and a lower complexity, because obviously if you have many different devices that need to speak to each other, it can get quite involved to set that up and to have things running reliably for years. Then we have the automatic synchronization to the AC source. So regardless of whether you're actually using an AC source or not, as soon as you connect something to the AC input of the AnyGrid, it will automatically synchronize. So it will see that there's an AC source there, there's a voltage there, it will check if the voltage is correct, it will check the frequency, and then it will adapt its own frequency to the frequency of that AC source if it's within the permissible window. So it really takes all of the guesswork out of synchronizing to AC sources, and it just means you don't need to have external synchronizing switches and things like that. Then there's no need for any inter-unit communication, except for obviously if you're using more than one of these AnyGrid units, where the communication is very simple. We have a very easy programming, a very easy definition of priorities, much fewer cables in the system, fewer fuses, fewer pretty much everything. And you can get all of your data in a single unit. And then finally, I think the most important point is it's set and forget. You just set the system up and it will just do its thing. You don't really need to care much about it. I'll just look at some of the questions you've asked in the meantime, because some questions have come in. The first one is how we connect the AnyGrid inverter to the Phocos Link app. Like I said, this is a Bluetooth app. So the display unit of the AnyGrid has an integrated BLE chip, and you can simply connect to that like you would to any other Bluetooth device. You put in your passcode, and then as soon as you're within range of that, you can just open up your Phocos Link app and you'll see everything that's happening in your system. The warranty period is 2 years. Reliability numbers, that's always very difficult if you have a reasonably young product. I mean, we brought this out now in June, And we've shipped out a few hundred systems, and so far we haven't had one come back. So it's a little bit difficult to say. But from our internal reliability testing, we're expecting maximum failure rates of well below 0.5% within, obviously, the warranty period. Then another question is whether the 120-volt AC devices will have the same programmability features. Yes, they will. And yes, you will be able to change the nominal AC output voltage to 110, 120, and 130. So getting back to the presentation, some more benefits are the ecosystem around the AnyGrid. So we have support for PylonTech lithium iron phosphate batteries. They have 48-volt batteries, so this is only valid for the 8-volt model. The 24-volt model, PylonTech just doesn't have 24-volt batteries for those. But for the 48-volt model, there's a special cable. You can ask for that from Phocos. We have that ready for you, and then it becomes pretty much a plug-and-play affair between the AnyGrid and the PylonTech batteries. We will also implement further lithium battery protocols as we enter negotiations with various lithium battery manufacturers. Then, as mentioned, we have the Phocos Link mobile app. We're also working on remote monitoring, but I can't give you any dates on that yet. So, in other words, connecting this thing to the internet and having a platform for remote monitoring, it's definitely on our roadmap, and we're working on that. But again, I can't give you any dates on that yet. Then we have very extensive documentation and training and technical support. We have reliable help from our side to help you for sizing the system. And we've been around for, well, almost 20 years now. So we know what we're doing, especially in the off-grid world, and also increasingly in the grid world as well. Now, arguably, maybe the most important benefit of this device is the high PV input voltage. If you want to compare this to some of the other off-grid inverters out there, which may or may not interface with the grid regardless, first of all, most of them don't have any charging from PV. You will need to connect them to an external charge controller or to a grid inverter for AC coupling. And those that do have MPPTs, or just generally virtually all of the off-grid MPPTs, they will have voltages for 48-volt batteries up to about 150, maybe 200 volts, but that's pretty much, like, there's some exceptions, but they tend to be extremely expensive, where you go into the hundreds of volts. So this device, if you paid attention in the beginning, we can handle up to 450 volts on the PV side. And we have an MPP voltage range of 120 to 430 volts for the 5K, and of 90 to 430 volts for the 3K model. So you have a lot of flexibility there in terms of your minimum and your maximum string length. So again, comparing this to like your typical off-grid charge controller, if you're working with something that has around about 150 volt open circuit maximum voltage, it means that if we're working with 60 cell PV modules, which I think are pretty much the cheapest worldwide, we will have 5+ strings if we're talking this kind of power class, like around about 5 kilowatts of PV power. And what will that mean? Well, as soon as you have more than 2 strings, you need a combiner box. Combiner box is basically, first of all, physically bringing together all of these multiple strings together and putting everything onto 1+ and 1-, which you then feed into your charge controller. And then also, you will need string fuses or diodes because there could be a reverse current situation between various strings. Virtually all the crystalline PV modules I know will accept up to 2 strings without any of these measures. So that really is one of the main ways you can save money with the AnyGrid, is by just saving on the number of strings you have, reducing those 5+ strings down to 1 or 2. And if you do that, you will just need standard Y cables if you're using 2 strings, and that's it. You don't need a combiner box, you don't need string fuses, you don't need string diodes and all those other things, which tend to add quite a lot to the system cost. So some other benefits of this higher PV voltage are you have much smaller cable cross sections to deal with. Coming from a combiner box, if you're dealing with 5 kilowatts at let's say around about 100 volts, you're going to be dealing with 16 millimeters squared. I'm not sure what that is in American wire gauge, but it's definitely a lot more. It's about 4 times as much than what we have here. So you can deal with very small cable cross sections, and pretty much the cables that come with your PV modules are all you need. You're not going to have to increase the wire cross section from that. So that already is a big cost saver there. You just save a lot of copper. Then, like I mentioned, you don't need a combiner box, which will add several $100s typically to your installation. No string fuses, no diodes. I've mentioned that. You generally have a lot less cables coming into your building, because if you're working with this traditional setup, either you have, in this case, 5 pairs, so 10 cables running into your home. So that's a big hole to drill to the outside world. Or you have your combiner box outside and bring in just the common positive and negative, in which case you still have thicker cables than for the AnyGrid. And on top of that, your combiner box now needs to be waterproof, UV proof, etc., because it's sitting outside. So those are the trade-offs you would have with the combiner box. You don't have any of that with the AnyGrid. Now the extensibility. I'm really running short on time, so I hope you don't mind if I don't answer your question right now. I'll answer them at the end, because I'm sure some people will have to leave on time. So I'll just push that towards the end. I'd like to look at extensibility as the last topic that's, let's say, a little bit less technical than the final 2 topics. For extensibility, you can see as a recap here your typical system, how it would look with the various optional components in your system. Now, if we want to have more power than what one AnyGrid can deliver, regardless of whether it's a 3 kilowatt or a 5 kilowatt model, we can hook up to 9 of these together. And we're very free in how we hook them together. We can have all units on a single phase. So we can have a single phase system with 45 kilowatts of synchronized AC power on a single phase. Or we can hook these up in 3-phase. And even if we hook it up in 3-phase, then we can even choose asymmetrical phases. So an example I give here is we might have 7 units on phase number 1, and just a single unit on phase 2, and a single unit on phase 3. And this might be a reasonable scenario if you're working with a large home, for example. You might have a lot of single-phase loads, but you'll have a couple, 3-phase loads. And you have those last 2 inverters just there for those, like your circular saw and maybe your oven, which might be typical 3-phase devices that will be running on these other 2 inverters. And all of your single-phase devices will be connected to the first 7, which will give you plenty of power on that single phase. Of course, you can also have symmetrical phases. Really, the only important thing is that you can have up to 9 units hooked together, so not more than 9. And that you must have at least 1 unit per phase. So if you're working with a single-phase system, of course, you can go from 1 to 9 units. And if you're using a 3-phase system, you need to have at least 1 on each phase. So obviously, you need to have at least 3 units. All the necessary communication and interface cables are included with each AnyGrid, so there's no need to order anything special if you want to have systems with multiple synchronized units. There is a small caveat if you're using more than 1 unit, and this is less pronounced on a single-phase system, a little bit more pronounced on a 3-phase system. The switching time increases from 10 milliseconds to up to 50 milliseconds. Like 50 milliseconds is the worst-case scenario. Typically, it'll be somewhere between 10 and 50 milliseconds. Again, most computer power supplies will handle power outages up to 50 milliseconds. So we are still within spec for the majority of your loads. Here is what this looks like. On the left bottom here of the unit, you can see these green. These are green connectors. These are analog form of communication. They are just for parallel systems. So if you're using more than 1 unit per phase. And here we have all of the other communication. So what this means, I have a few examples for you here. If we set up 5 AnyGrids on a single phase, then we need the green cables and the gray cables. because again, as soon as we have more than one unit on a phase, we will need the green cables. So that's what we have here. And either way, we definitely need to have the communication cables between the units where we synchronize all the settings, where if there's a phase shift, if you're using a three-phase system, that's where the information travels for the phase shift, etc. So what's important for you is that they must all be on the same battery. You cannot have multiple batteries with these inverters. They will throw up an error if you do try that. And there's very few cases where I think that would make any sense. You also need to have breakers for each unit individually, just for the sake of safety. Now here's a further example, in this case, a three-phase scenario. So I've purposely taken an asymmetrical scenario to show you again that you can use different numbers of units per phase. So in this case, we have 7 units on the first phase and 1 unit each on the second and third phase. So here, if you look at the interconnections between the units, they're the same on the gray side. You're always hooking up to the direct neighbor or 1 over between the communication cables. And that obviously makes sense because if you were to have to connect from unit number 1 to number 9, you could end up with many meters between the units and the cables might not be long enough. So it makes sense to have it hooked up like this. And then what you might notice is on phase 2 and phase 3, we have no green cables. Because like I said before, you only need the green cables if you have more than 1 unit per phase. On phase 2, we have just 1 unit, and the same thing goes for phase 3. Now, for those of you that are not interested or less technical, feel free to leave now. These last topics on sizing and grounding are for the more technically oriented. So for those that are leaving, thank you for joining. Again, we will send the presentation out to all of you, so even if you do leave, you shouldn't miss any of the critical details on that. So I'll just keep going now so we don't lose any time. For the system sizing, one of the first things is obviously the battery size, if you do use a battery. And I think the most important thing to keep in mind there is the minimum battery size. We recommend that you use, if you're using lead-acid batteries, regardless of whether they're gel, AGM, or open type batteries, liquid electrolyte, we recommend at least 200 amp hours per unit. So if you're using 2 units, you need to have at least 400 amp hours for the 48 volt system. If you're using lithium batteries, then typically you will have ratings for how many amps charging and discharging current are allowed on the batteries. So you can check that and make sure that it's compatible. As a reference here, the maximum charging current is 80 amps, regardless of whether it's PV, grid, or mixed. Again, you saw before, we can reduce that charging current if you need to cater towards smaller batteries. For the discharge, we have much higher currents because we're dealing with an inverter which can potentially be used off-grid, which means that in such a scenario, it would not be supported by a second energy source. So all of the 5 kilowatts or 10 kilowatt peak, we need to be able to draw those out of a battery if there's no PV available, for example. So that would mean continuous rating 140 amps, and peak rating to handle the 10 kilowatts for 5 seconds would be 280 amps per unit. Now, if you do want to use the PylonTech batteries, we're compatible with all of the 48 volt models. You can check with Rita Ping from PylonTech. Her email address is here if you want to source those in whatever country you're living in or where you're building the project. If you're using lithium batteries that are not from PylonTech, then for the moment, we don't have any others implemented in terms of communication. So you would need to make sure that they have a battery management system that does not require a communication with the inverter. For the PV array, the PV array must meet these requirements, and if it does, then it's automatically good for the system. This is specific to the 48 volt models. Obviously, there's only small minor differences for the 3 kilowatt 24 volt model. Namely, the minimum PV voltage is lower for the 3 kilowatt model. It's 90 volts MPP instead of 120 volts. So typically, this is the correct order in how I would size such a system. I would always look at the minimum PV voltage of the inverter. So in this case, we have 120 volts for the 48 volt 5 kilowatt model. and at the maximum PV voltage, which is 430 volts MPP and 450 volts open circuit. And you need to make sure that you never surpass the 450 volts, even if it's cold outside. You might have very cold winters, and you probably know PV modules will output a higher voltage when they're cold, so you need to take that into account for your region. Then we have a maximum usable PV current of 18 amps. So in practice, it just means 1 or 2 strings, and that's how you build your system. For each string, you have a minimum of 5 PV modules if you're working with 60-cell crystalline PV modules. So that means your minimum power for the 5 kilowatt unit is about 1.25 kilowatt peak, and the maximum is 11 PV modules in series. If it's really warm in your region, you never have cold winters, you might be able to fit in 12, but that's living at the edge basically. So I would recommend up to 11. And that means you can have up to 2.75 kilowatt peak per string, probably even a little bit more if you're using 270s or 280s as PV modules. And of course, you can use 1 or 2 strings, so that will give you up to 6 kilowatts peak that you can connect to the AnyGrid inverter. For the 3 kilowatt model, it's about 2/3 that, roughly. Make sure that you don't have more than 6 kilowatt peak connected. Nothing should break, but it typically doesn't make a lot of sense in terms of an investment to have more than 6 kilowatt peak connected. And there's a limit to what you can test. So we've tested it up to 6 kilowatt peak, and we know that works. And up to 4.8 kilowatts are truly usable by the inverter when the battery voltage is high and when you have the maximum solar irradiation. For the AC generator, things get a little bit cryptic, so I'll save that as just a pure dictionary for you if you need to look it up, if you want to choose an AC generator to fit to the AnyGrid. What is important, I think, is to have a certain minimum generator size. And we recommend to have 1.5 times the nominal power of the inverter as a generator size. And the reason is quite simple. When you're working in AC or in grid mode, even though technically speaking this is not a grid, it's an AC generator, then you need to be able to power all of your loads, and at the same time, if you're charging your battery, you need to be able to do that at the same time simultaneously. So if you're charging your battery with say 2 kilowatts, then you need to make sure that you can have another 5 kilowatts to power your loads. So you'll end up with about 7.5 kilowatts of power that your AC generator should be able to deliver. Now the final subject is grounding, and at the very end we have some recommendations as well. For grounding, grounding is obviously very important for safety. I don't have the time to explain why, but those that are installing the system should know. The mandatory grounding on the AnyGrid is both on the AC input and the AC output. Obviously, if you're just using one of the two, then you just need one ground point. They're connected internally. So you must absolutely connect those for safety. And you need to make sure that you have a low impedance ground at your area of installation. Then typically, and this really depends on your country, what kind of a grounding scheme you have. So I'm looking at TNCS here, which is common, I think, in most parts of the world, certainly is in Europe. In this kind of a scenario, to protect people, like the actual users from electric shock, you would use a residual current device, an RCD. And in order for that to work, there needs to be a connection between the neutral and the ground. And if a typical off-grid inverter is working in off-grid mode, as I told you before, it disconnects neutral and line from the grid. So basically this bridge you have here between neutral and ground no longer exists, because the whole first part is basically cut out of the system. So what the AnyGrid actually does internally is that's the last point here, it automatically bridges the neutral and ground wires. And that will simply ensure that if you're disconnected from the grid, that this bridge, which is absolutely important for the residual current device to work at all, is then made inside the device on the fly to make sure that your residual current device will always protect people from electric shock if ever they touch any of the phases or the neutral conductor. So the upside of this is that you don't need to have like a ground fault detection device or expensive equipment like that. An RCD, you will get that in any hardware store for $10 to $20. Then for grounding the DC side, really, like I said, the only mandatory grounding is the ground on the AC of the inverter. The rest here is voluntary, or, well, depending on your legislation, it might be mandatory. I think the one thing that really does make sense to ground is the frame of your PV modules and the structure they're mounted on. And this doesn't have any effect on the device whatsoever. You can ground your battery negative or your battery positive. For PV, you're not allowed to ground either positive or negative. So battery, you're completely free to ground as you wish. For PV, you can only ground the frame of the PV modules. Then for the surge protection, as almost any inverter from any respectable brand out there, there is obviously some surge protection integrated into the unit on the PV side and on the AC input side and the AC output as well, battery as well. But all of these things have their limits, of course, and an external surge protector will always do a lot more and has a lot more, let's say, higher current ratings to be able to swallow a lot more energy and then to point that towards ground. So I would always recommend a surge protection, at least on the PV side, you'll see in the next slide, but also on the AC side. Again, this doesn't cost much. It's like in the realm of like $20 to $50 maybe. This is a very standard component, the surge protector for the grid side. So this is if there's any lightning or anything in your area, and you have a high voltage peak which is coming in through the grid, or if you have a AC generator, for example, this surge protective device will cancel that peak. So our recommendation, we have two models listed here for various different scenarios that you might have depending on the quality of the grid. And then for the PV side, we recommend this model. This is it's very important to have the correct rating for this for the SPD coming from PV, because I know a lot of people make the mistake. They think, oh, I'll just use any old SPD that I'm using for a grid-connected inverter, where a lot of these will actually only start protecting for voltages above 1,000 volts. So you can imagine this already has a very high maximum PV input voltage of 450 volts. But if you're connecting an SPD, which will only start protecting above 1,000 volts, well, that's still a difference of over 500 volts. So it's not going to do any protecting, because if the voltage rises to, let's say, 800 or 900 volts, the SPD is still not doing anything, and the inverter is already taking damage. So if you do install an SPD, which I do recommend, then do make sure you take the right one, because otherwise it will simply not function. It will not do its job of protecting from high voltage peaks. And that's all we have for you today. So for those of you that don't have any more questions, I want to thank you very much for joining. Keep your eyes open. We might have future sessions like this, future webinars. I'm sure that once we release the 120 volt models for the, well, predominantly for the Americas market, which, by the way, they will always also be UL approved, which is, of course, very important for your markets. We'll probably repeat a webinar such as this one, which will be focused a little bit more on the 120 volt systems out there, on the split phase, etc. So yeah, just keep your eyes open for that. We'll be sure to post it on our LinkedIn page and also on our website.
For more videos and information, go to www.phocos.com. Phocos, making reliable energy access possible. Anywhere, anytime, any grid.